Last day of this chapter, we're going to jump to section 3.5 in our book, and we're going to talk about infinite limits. Infinite limits. Limits as x approaches infinity. We'll get to that second goal in a little while. Limits at infinity. What we're really looking for is x's get really, really, really large, or really, really, really small. But, you know, huge numbers, whether they have a positive or negative sign on it, isn't going to end up making that much of a difference to us. As x goes toward infinity, let's see, so as x's get really, really, really large, meaning they're working their way down this direction someplace, or negative infinity, they're working their way down that direction someplace, if that limit, if the function heads toward a specific y value, meaning let's say that y equals L is right there, and this function, as the x's get really, really large, kind of starts to level off like that. Well, what have we just found? We just found that this function has a horizontal asymptote at that value. And the reverse, the same thing is true. If it's headed this way and starting to level off, what we found is we found a horizontal asymptote. So again, remember, every limit's result is a y value. So if either the positive or the negative infinity head towards some specific y value, then what we found is we found a horizontal asymptote. How do we find that? Well, we go through a little bit of a process. We're going to use this theorem right here. This theorem says is x's head toward infinity. Again, remember, now the x's are headed toward infinity. And we've got only one x in that little equation that we found there. So we've got a number c. It has nothing to do with x. So let's say I call a generic 5 or something like that for c. Well, as x's get huge, if you take 5 divided by 100 to a power, or 1,000 to a power, or 10,000 to a power, you're going to have a number on the top that stays the same size while the denominator gets bigger and bigger and bigger and bigger. You're going to have 0 for a result. If we do the same thing as the x's head toward negative infinity, again, the only thing that's going to change potentially is the sign, but even if the sign changes and the denominator gets huge, the numerator stays the same size, we're still going to end up with 0. We just may be coming at it from the opposite side because of the plus or the minus. So how do we use that? Well, first limit. Limit as x approaches infinity. We've got two terms here. We've got a term 5 and we've got a term 2 over x squared. So let's rewrite this limit so we can handle them separately. Limit as x approaches infinity of 5 minus limit as x approaches infinity of 2 over x squared. Let's get some quantities in there. Well, that first limit, limit as x approaches infinity of 5, that limit has nothing to do with, it's going to be 5 all the time. X doesn't play a role because it's always 5. So it doesn't matter how big x gets because this result is going to stay 5. And the second one, as the x's get bigger, we're applying this first theorem, the first part of this theorem right here, because we've got a number 2 divided by a quantity x squared, and because that x squared on the bottom is, we're using huge numbers in place of that x and then squaring them, that means we're going to end up with a 0 effectively as a result. What's this limit going to be? That limit is going to be 5. Now, what does that mean? Why did we do all this? Well, what we effectively just found, we've answered the question. The question said find the limit. Why will we find a limit? A little foreshadowing for you. What we would have just found is that this original function would have a horizontal asymptote at y equals 5. Now again, the question didn't ask us to find horizontal asymptotes. It asked us to find the limit, but we're trying to kind of set us up for what's coming next, or what's coming down the road. Second one. You'll notice this time we don't have two nice terms. We've got a, kind of a little bit of a rational expression going on here. So we've got to go through a little process in order to hopefully turn problem number 2 into something like problem number 1. And the way we're going to do this, first thing we're going to start with is we're going to locate the highest power of x in the denominator. Now again, it's got to be a limit that heads toward infinity, which is good. That's what we've got. Locate the highest power of x in the denominator, which in this case is x to the first, and then multiply both the top and the bottom by 1 over x to that power. So we're going to multiply top and bottom by 1 over x. And if we rewrite the problem, then this is what we're going to create. Limit as x approaches infinity. Numerator is going to become a 2 plus a 1 over x. Again, I'm distributing the 1 over x. So 1 over x times 2x would give us the 2. 1 over x times 1 would give us the 1 over x. Denominator, 1 over x times x would give us a 1. 1 over x times 2 would give us a 2 over x. And now if we take a look at this, what we just did is we just created a problem number 1 in the numerator and a problem number 1 in the denominator, and we're going to handle in the same way. Or the thing that's going to be nice is anybody that ends up with an x in its denominator is effectively going to turn out to be a 0. So if that's the case, we're going to end up with a limit here of 2 over 1, or just plain old ordinary 2. And what we've found, if the question asked us, is we would have found a horizontal asymptote at y equals 2. Problem number 3, again, same thing. Let's locate. Again, when limit as x approaches infinity, let's locate the highest power in the denominator. If we've located that, so now we're going to multiply top and bottom by 1 over x squared. If we do that, rewrite the problem. Limit x approaches infinity. Numerator 2x times 1 over x squared would give us 2 over x. 1 times 1 over x squared. X squared times 1 over x squared. And 2 times 1 over x squared. And let's see what we've got. Anybody that's got an x in the denominator is effectively going to become a 0. So we're looking at a limit here of a 0 over a 1, or of course a 0. And if we would have asked where would that function have horizontal asymptotes, it would have a horizontal asymptote at y equals 0. Last one, let's do the same thing. Locate the highest power of x in the denominator. Looks like x to the first. Let's multiply top and bottom by 1 over x. If we do that, limit as x approaches infinity of, let's see, x squared times 1 over x would be x, plus 1 times 1 over x would be 1 over x, over x times 1 over x would be 1, and 3 times 1 over x would be 3 over x. Anybody who's got a 0 in the denominator is going to disappear. What do we got left? Well, we've got x on the top. If we directly substitute an infinity in place of that, we've got infinity, and on the bottom we've got that 1. So infinity divided by 1 is going to be an infinity. And what we'll find in the next video is that that's going to not give us a horizontal asymptote. It's going to give us something else. So there are your limits at infinity, and we'll work on some more stuff next.